morning, everyone. Welcome to our talk. Excited to be here in one of the first sessions of the conference. Our session topic is migrating and optimizing large-scale streaming applications with Databricks. We're going to cover a lot today, so we won't be able to take questions during the presentation, but we'll be happy to take questions at the end. And you can always find us on LinkedIn if you have burning questions we couldn't get to today. I'm Sharif Dagmi, lead software engineer at FreeWheel and tech lead for the project. And I have the pleasure of being with Dongwei today.
Hi, my name is Donghui Li. I'm also a lead software engineer at FreeWheel.
Let's start with a quick overview of the session's topics. First, we'll introduce FreeWheel, beeswax, and programmatic advertising for people who are new to it. Then we'll talk about our beeswax data platform and how we redesigned, redeveloped, and migrated our large-scale streaming application that's part of this larger data platform. After that, Dongwei will talk about how we implemented a robust monitoring and observability solution for this new streaming application. And he'll discuss various interesting performance optimizations we implemented. Following that, we'll talk about Databricks features that improved our development experience. And we'll share future Databricks-related work we have on our roadmap. Let's begin with the introduction. We are both from FreeWheel, which is a Comcast company. If you work in ad tech, then you've probably heard about FreeWheel. But if not, I'm happy to give you a quick overview. FreeWheel provides comprehensive ad platforms for publishers, advertisers, and media buyers. We make it easier for buyers and sellers to transact across all screens, data types, and sales channels. We have products for both the demand side and supply side of advertising. We serve many of the largest companies in the US and Europe, and we power advertising for many of the biggest sporting events. Now let's talk about beeswax. Beeswax is FreeWheel's programmatic buying platform. I think the best way to explain what that is for people who haven't worked in ad tech is to start with a programmatic advertising 101 with a focus on real-time bidding. On the right side, we have the demand side of advertising, meaning the ones who buy the ads, such as advertisers, trading desks, and other media buyers. On the left, we have the supply side, who sell the ad inventory, such as publishers, programmers, broadcasters, and distributors. In this graphic, we used an advertiser to represent the demand side and a publisher's website to represent the supply side. But it could also be a mobile app or a video streaming platform that serves ads or something else. The demand and supply sides don't communicate directly in real-time bidding. There are multiple layers in between in the form of demand-side platforms, or DSPs, supply-side platforms, or SSPs, and ad exchanges in the very middle. To put this into context for people from other domains, this is actually very analogous to electronic trading in finance, where you have the buy-side and sell-side market participants instead of publishers and advertisers, with brokers and exchanges in between, and financial instruments being traded instead of ad inventory. Okay, now going back to the graphic, on the left side is you, on your computer or mobile device. Let's say you visit a publisher's website with ad space, represented by step 1. The publisher doesn't solicit ads from advertisers directly in programmatic advertising. Instead, a very complex multi-stage process takes place and completes in a fraction of a second. In steps 2 and 3, the publisher sends an ad request message to the ad exchange via an SSP. Then the ad exchange starts an auction, and in step 4, it sends bid request messages to multiple DSPs, inviting them to bid on behalf of their advertisers. In step 5, the DSPs reply by sending bid response messages to the exchange. And in step 6, the exchange selects the highest eligible bid as the winner of the auction. The winning ad is then served to your device in step 7, resulting in an ad impression. Like we said, FreeWheel provides products for both the demand and supply sides. And beeswax is FreeWheel's programmatic buying platform on the demand side. It's a DSP and more. And we'll go into more details about this next. What exactly does beeswax do? Beeswax enables demand-side customers, such as advertisers, to plan and execute their ad campaigns, bid on ad inventory using our advanced real-time bidding technology, and monitor, analyze, and optimize their ad campaigns. It's a best-in-class buying platform that provides media buyers with full transparency with log-level granularity, better customizability, and more control over their ad campaigns. Our key offerings include a highly customizable out-of-the-box DSP offering and a bidder as a service, which gives customers their own fully customizable bidder deployed in their own cloud instance as a form of single-tenant architecture. Within Beeswax, we have the Beeswax Data Platform, which contains the streaming application that is the subject of this presentation. This diagram depicts the high-level architecture and data flow within Beeswax Engineering's different components managed by different teams. I wanted to use it to give you a visual of where the data platform lies within the Beeswax Engineering ecosystem. You can see the data platform sits right behind the serving platform, which interfaces with the exchanges and does the real-time bidding. Then, the serving platform's front-end server relays those auction-related ad events to the data platform. The serving platform also has an event server, not shown here, that collects post-auction events such as impressions, clicks, and conversions, and relays them to the data platform as well. This enables the data platform to provide reporting, analytics, and streaming ad log delivery for our customers, and to store the data in our warehouse that acts as the single source of truth for our data. I think one of the keys to understanding a data processing system is to understand its data. So here's a list of the main ad event types received by the data platform. The most common ad events we get are bid requests. Then comes bid responses. These two are sent by the front-end server we discussed earlier. And then we have post-auction events that include impressions, clicks, activities, and conversions. These are also known as win events, and they come from the event server previously mentioned. Impressions and clicks are self-explanatory at this point, but activity events are generated when a user interacts with the video, such as by pausing, resuming, or skipping back. Conversion events arrive much later and are generated when the ad converts the user, such as by buying something after viewing the ad. And finally, there are several other much less frequent ad event types we don't need to go into. This slide summarizes what the data platform does. But instead of going over all this text, the best way to describe the data platform is through an architecture diagram, of course, because an architecture diagram is worth 1,000 words. The diagram shows the architecture of the Beeswax data platform before the migration. Everything was and continues to be on AWS. Everything in yellow is an external data provider to the data platform. And everything in green is external customer-facing output. Apologies to anyone here with color blindness if I didn't get the colors right. I'll try to use the pointer as well. On the left side in yellow, we have our two main data sources, the front-end server, which sends us auction-related events, and the event server, Honeypot, which sends us post-auction events. They write those protobuf encoded ad events in real time at over 5 gigabytes per second to the data platform's intake Kinesis stream called Nectar. For people not familiar with AWS, Kinesis data streams are similar to Kafka. Here we're using it mainly to act as a distributed queue and buffer between the source and destination, which can produce and ingest data at different rates. Unsurprisingly, as you can see, at Beeswax, we like to use a lot of B terminology for naming our applications. Nectar, Honeypot, Honeycomb, Buzz, and of course, Waggle, in the big blue box in the center, which is the large-scale streaming application that we recently migrated. In case you're wondering what Waggle means, it is the name of a dance that honeybees perform to communicate with each other. Waggle is a massive application with over 30,000 lines of code. After reading the streaming ad events from Nectar Kinesis stream, Waggle decodes and parses them, then filters, transforms, anonymizes, and joins them. And finally, routes them to hundreds of heterogeneous destinations, including S3, Kinesis, and HTTP endpoints. Up in pink is the Aerospike distributed key value store that Waggle uses for caching events in order to join related events that arrive at different times, such as bid requests, impressions, and clicks that belong to the same auction. Because it relies on Aerospike for maintaining state, Waggle itself remains stateless. To the top left of Waggle are customer log configurations that Waggle uses to determine which ad logs to send to which customers on which endpoints. Just to add some context, we call event-level data add events on the way in, and we call them add logs on the way out. There are also internal endpoints, such as a Kinesis data stream at the bottom left that gets read by our Beetle application that produces real-time campaign stats. Waggle also outputs certain ad events to metamarkets, which enables interactive multidimensional analysis on ad inventory. Another very important output by Waggle is our internal S3 data lake in the middle, from which they are automatically loaded into our data warehouse, shown in pink, to be further processed by over 60 Airflow pipelines to prepare event-level tables and aggregate reports that customers can access through a Looker UI, an API, as well as Snowflake shared tables and batch deliveries of flat files to customers' external S3 buckets. Finally, auctions are sampled and loaded into an Apache Druid cluster right here. This Druid cluster is used as our low latency data store by our forecasting application to enable customers to forecast ad inventory availability and campaign fulfillment using our proprietary online machine learning models. Also worth 1,000 words are pictures, of course. And I wanted to provide a few visuals to better illustrate what our data platform does. Here's a dashboard that we build and maintain and provide the data for. It gives advertisers high-level stats about their campaign spend and performance over a chosen period. And these charts show real-time bidding and winning stats, as well as campaign spend over a chosen look-back range. And finally, here is a MetaMarkets Explorer page that provides almost instantaneous interactive analytics over auctions, bids, and wins, and allows advertisers to explore, filter, and drill down by many dimensions, such as ad site category, device type, geo-region, deal ID, ad size, ad position, etc. I believe another key to understanding a data processing system is to understand the scale of its data. Every second, Waggle receives and processes 3 million ad events on average at over 5 gigabytes per second, which translates to over 4 terabytes of input data processed per day. Okay, now let's start getting into the meat of the presentation, beginning with the redesign and migration of our streaming application, Waggle. We already covered all these points in the data platform architecture slide, so we can move on. I just wanted to provide a textual summary in this slide for people watching the recording later. Let's go back to the architecture diagram for a second to show you exactly what changed in the new architecture. As we said, we have Waggle as a Java KCL streaming application in the big blue box in the center. After the migration, we swapped out Waggle with the creatively named Waggle v2 that now uses Spark Structured Streaming instead of the Kinesis client library and runs on a Databricks job compute cluster instead of an EC2 cluster partially managed by an external service. The new Waggle v2 is currently using a Databricks Classic setup, meaning clusters run in our own AWS account. But we are considering adopting Databricks serverless when it supports streaming workflows like ours. Instead of Java, Waggle v2 uses a mix of Scala and Java, and more on that later. Another change we did is migrating customer log configs to the Databricks data lakehouse. They are now stored right here. They are now stored as delta tables in the Unity catalog. This brings log configs closer to the now Databricks-based Waggle v2. And furthermore, can now be queried using SQL, which wasn't possible when they were stored as protobuf objects in S3. This makes their content more explorable and available not just to engineers, but also to other non-technical stakeholders, such as product managers and customer support. We're actually considering migrating more of our data stores to Unity Catalog to make use of its powerful features and to achieve synergy between different Databricks solutions. Moving on to redesign and migration objectives. What did we try to achieve with this redesign, redevelopment, and migration of our streaming application? We targeted several KPIs for improvement. I'll just outline them here quickly and leave the detailed description for later when we share the results. These KPIs are system stability, certain cost inefficiencies that needed to be cut down, and avoidable maintenance and troubleshooting time that needed to be reduced to enable engineers to focus on value-adding tasks. And 4 data quality dimensions: accuracy, completeness, timeliness, and delivery semantics. And the last one is better known as at least once, exactly once, or at most once data delivery guarantees. What is the strategy we followed to improve those target KPIs? We re-architected the system using top-down design now that all the requirements are known. This fixed the inefficiencies that were introduced into the system because of its gradual development over several years, with new features and logic bolted on top one by one at different stages by different developers in an incremental manner without a holistic view. This top-down redesign that is now possible, now that the bigger picture is clear, allows us to remove this accidental complexity that was gradually introduced into the system, leaving the system with only its essential complexity. At the beginning of the project, we evaluated different stream processing technologies, including Apache Flink and Storm and others, and found that Spark Structured Streaming on Databricks suited our use case the most. So we went with it. We correctly predicted that migrating from KCL to Spark Structured Streaming would eliminate memory leaks inherent in KCL and significantly reduce instance failures for multiple reasons, as well as eliminate concurrency issues we kept facing like deadlocks and starving threads. It would also delegate more infrastructure management to Databricks, such as AMI upgrades and system library updates, and this freed up some of our developers' time. Moreover, Spark Streaming has built-in microbatching for data from input through output, which suits our use case and allows us to get rid of the custom logic we had to build before when we didn't have that out of the box. Our previous KCL-based application was written entirely in Java. Since Java and Scala both run on the JVM and are interoperable, we were able to keep some of the Java code while migrating some to Scala and writing new code in Scala, and having both Scala and Java coexist in the same application. We made this pivot to Scala because Scala allows us to write clear, concise code using the functional programming paradigm with immutable data structures, no side effects, and robust, hassle-free concurrency. This further improved system reliability, testability, and maintainability. Actually, all 3 last bullet points on this slide helped improve system maintainability. Okay, now let's see how this redesign and migration strategy fared. System stability. Out of memory and other errors resulting in instance failures that were happening on a weekly basis are now a thing of the past. We rarely, if ever, get those instance failures nowadays. Those failures often resulted in lost work that needed to be reprocessed, resulting in unnecessary costs. But since this is no longer taking place, we no longer have those cost inefficiencies. Another cost inefficiency that was happening was when an instance kept running, but its thread were deadlocked or starved. And so the instance was running and costing money, but not producing anything. That's another one of several cost inefficiencies that were eliminated. Those frozen instances often needed manual intervention to diagnose and terminate, wasting developers' time, but that's no longer the case. Also, developers no longer have to spend time on maintaining infrastructure, such as time-consuming AMI upgrades and resolving complications that they often result in. This also reduced wasted time. We used to spend over 10% of our time just on maintaining and troubleshooting Waggle, and now this is down to almost 0. All right. As for data quality, we already had decent accuracy and completeness at over 99.95%, which is excellent for ad tech. But we wanted to fix the few malformed, non-complete, and missing records, and we managed to do that. So now both accuracy and completeness have improved. Data timeliness has also improved because we are no longer losing instances and having to reprocess, which used to delay some data. And finally, we moved closer to exactly once guarantees because we are no longer having to reprocess starting from previous checkpoints, which usually results in duplicating some of the output. We were fortunate enough to achieve all of our objectives. Now let's get a little bit more technical with the inevitable code slide. This is a high-level outline of our application's streaming logic written in Scala. Of course, this is an oversimplification, but I just wanted to showcase some of the Spark Structured Streaming constructs we are using and explain why we're using them. As you see on line 1, we are first getting a Spark streaming data frame from the Kinesis stream. On line 2, we create a data stream writer object from the streaming data frame and set the trigger interval for targeting 60 seconds for each microbatch in this example. On line 4, we invoke the for each batch method on the data stream writer object. For each batch is a higher order function that takes in other functions as arguments. In this case, it takes an anonymous function that is defined in line. The curly braces are just Scala syntactic sugar we can use for block expressions. For each batch is used when there doesn't exist a streaming sink for your storage system or when you want to output to multiple destinations. For each batch gives you a data frame to work with so you can perform all batch operations available to data frames on streaming microbatches. Streaming data frames have less operations available to them than batch data frames. So for each batch helps overcome this limitation. On line 5, we cache the data frame so we can reuse its contents without recomputing them, which improves performance when you're outputting to multiple destinations. For simplicity's sake, in this code we are only showing the S3 output part, and even that part is only summarized here. Since different rows in the data frame are going to different S3 destinations, we wanted to first group together rows going to the same destination so we can write them to one S3 object in one go. We also needed more control over the S3 writing logic than affording to us by the data frame API. For these reasons, we chose to use for each partition on line 9. Like for each batch, it's also a higher order function. Inside it, we are grouping elements by shared destination before writing them out to S3 using our custom S3 writing logic. Then we output to other endpoints and uncache the data frame on line 15. This strategic use of for each batch and for each partition with group by destination enables us to significantly increase the number of records we put into each S3 object. This decreases the number of S3 objects outputted and the associated overhead, which increases performance, reduces cost, and highlights an important benefit of the microbatching paradigm used by Spark Structured Streaming. And now, I'll hand it over to Dongwei to talk about monitoring and observability. Yep.
Do you hear?
Yeah.
Okay, all right. Sorry. As you know, monitoring is very important to gain visibility into how a system is working and to maintain its reliability and performance. There are a lot of challenges for a good monitoring solution, such as scalability, flexibility, and so forth. Traditional monitoring solutions often fail to address these challenges effectively. We use Prometheus for monitoring our application. Prometheus is a widely used open source tool. It has established itself as a powerful and flexible monitoring solution. It has a lot of key features, that make it very attractive. We instrumented an extensive array of metrics in our application using Prometheus and use Grafana for visualization and alert management. This diagram shows how Prometheus works for our Spark application. On the Databricks cluster, we spin up an HTTP server on the driver node and each work node. Using service discovery, the Prometheus instance finds all the nodes in the cluster and pulls for metrics from the HTTP servers periodically. The Prometheus instance aggregates metrics and pushes those aggregate metrics to Grafana Cloud. The Grafana dashboard queries Grafana Cloud for the metrics and displays panels on the dashboard. That's how the data flows. We also use metrics to define rules to send PagerDuty alerts so that support engineers can respond quickly to anomalies. Again, we are using Databricks Classic, where the cluster spins up EC2 instances. This architecture needs to be adjusted when we migrate to Databricks serverless. Just to give you some idea, I have some screenshots of our Grafana dashboard. These 4 panels show the current and the historical memory and CPU utilization of the entire Databricks cluster. Here are a few other Prometheus metrics we have for the application. We currently have more than 60 panels in the Grafana dashboard to monitor different components of the application. We measure the application's processing delay, execution time of each microbatch, incoming data rate, measurements of different outputs, etc. We stumbled upon a few things when we initially worked on metrics for the application. One thing that's worth mentioning is that Databricks launches each EC2 instance with 2 private IP addresses, primary address and secondary address. The secondary address is the one used by the Spark container. To scrape for Prometheus metrics, the secondary address is the one to use, not the primary address. However, we only get the primary address using Prometheus EC2 service discovery. To work around this issue, we added an EC2 tag for the secondary address and relabeled the IP address in the Prometheus job to replace the primary address with the secondary address. The screenshot shows how we configure relabeling for the Prometheus job. To get insights about the Spark platform, we also incorporated Spark job wizard metrics into our application. This allows us to monitor not only the application, but the underlying Spark platform as well. The 4 panels I showed previously for CPU and memory utilization use Spark job wizard metrics. Now about Databricks logs. We created another Grafana dashboard as a central place to view Databricks logs. The Databricks logs include standard out, standard error, log4j logs from the driver node and all the work nodes, as you can view them in Spark UI. This is done by first configuring the Databricks cluster to send all the logs to AWS S3, then ingesting the logs from S3 into Grafana Cloud. A Grafana dashboard is then set up to display the logs. Using the Grafana dashboard, we can now look up all the logs in one place with searching and filtering capabilities. Here's a screenshot of the Grafana dashboard for Databricks logs. On the top of the dashboard, there's a time range selector and other selectors and filters highlighted by the red boxes. The area in the green box contains logs from the driver node. The area in the blue box has logs from all the executors or work nodes. Now switching gears to performance optimization. We applied several techniques to enhance the performance our Spark application. I will highlight a few of them next. We use cryo serialization. Cryo is significantly faster than Java serialization. Based on a benchmark comparison we did using our own data, cryo is about 3 times faster than Java serialization on average. By default, Spark uses Java serialization. The screenshot shows how to turn on cryo serialization on a Databricks cluster. Memory optimization could be very application and data specific. We did a few things in our application to optimize memory utilization. We have a limited number of configuration Java objects. One of them needs to be in every row in the Spark dataset. So we built a lookup table for them and used simple identifiers to represent them in the dataset. We also made sure all the rows in the dataset contain only necessary information for the output and removed unneeded fields. We use an AWS Kinesis data stream as our input data source. A lot of Kinesis parameters need to be adjusted based on the use case to optimize the performance. In this slide, I listed a few of the parameters that we have optimized for our application when the microbatch interval is 1 minute. Max fetch rate is the maximum data rate for prefetching. We set it to 2, which is the maximum we can set. Max fetch duration is how long we buffer prefetch data. A larger max fetch duration gives us better performance. Since Spark can read data from Kinesis pretty fast, we set shards per task larger than the default to let each Spark task handle more shards. We force Spark to coalesce small partitions to bigger partitions by adjusting coalesce threshold block size. I'll use max fetch duration as an example of how we optimized those Kinesis parameters. Again, max fetch duration is how long we buffer prefetched data before the data becomes available for processing. The line in the picture is the Kinesis iterator age. If the iterator age keeps increasing, that means data in Kinesis is backed up and the application isn't keeping up with the incoming traffic. The picture shows that when we increase max fetch duration from the default value, which is 10 seconds to 20 seconds or 30 seconds, we could cut back the number of work nodes significantly, and the application was able to handle the incoming traffic just fine. For every parameter I listed in the previous slide, we did a study like this to find the optimal setting for our application. Spark itself is an orchestrator for parallel processing, but we added more flavor to it. On the driver node, we use a thread pool to process multiple data frames simultaneously. On the worker nodes, we parallelize tasks to write S3 files within our custom Java code. All we are doing is to maximize the resource usage and speed up processing. Another technique we use is caching. We cache not only data frames, but also AWS resources. One example is we got significant performance improvement from caching AWS S3 clients. We found that creating an S3 client with an IAM role assumed took about half a second in certain AWS regions. Obviously, caching them can save a lot of time if we need to use them frequently. In this kind of streaming application, every bit of time counts. One Databricks feature we haven't tried is stream pipelining, previously known as microbatch pipelining. We haven't tried it yet because it's only available in the serverless. We believe it will give us another performance boost when this feature is enabled. Just to show the effectiveness of parallel processing, these are the logs from writing S3 files for one data frame partition. The tasks to write these S3 files ran in a thread pool on a particular workload. Because these tasks were parallelized, writing all 51 files took just 2.7 seconds in total. If we ran these tasks sequentially, it would take more than 15 seconds. Parallel processing makes a big difference for those I/O-heavy tasks. After all the optimizations we did, we were able to cut the number of work nodes significantly to save costs. That's all I have for performance optimization. Now I hand it back to Sharif.
All right. Thank you, Dongwei. The next major topic is the Databricks development experience. Databricks provides many features that make development more efficient and convenient. These include intuitive APIs, such as the Data Frame API, which is simple and unified across batch and streaming applications, has a rich set of functions, and seamlessly integrates with the various data sources and storage systems. Then there's the Databricks Terraform provider, which allows you to quickly and easily define Databricks infrastructure and resources using code. And of course, there's the new Databricks Asset Bundles, which brings an IAC approach to CI/CD. They allow you to use YAML files to define jobs, notebooks, and other project artifacts. And they provide an easy-to-use CLI tool for deploying, running, and managing jobs. And notably, there are Databricks IQ-powered features, such as the Databricks Assistant and AI-generated comments, which we'll talk about next. The Databricks Assistant helps you generate, explain, and fix code. In this example, in which I was running code inside a notebook, when the code failed, the Databricks Assistant automatically popped up, saying that a -8 error codes under these circumstances indicated a network error when trying to connect to Aerospike, and suggested fixing the IP address, which was what solved the problem indeed. You can also ask questions to the Databricks Assistant in an interactive way, and it can provide useful code examples that save you time. Databricks IQ uses signals from across your Databricks environment to create context-aware generative AI models that make the assistant more accurate and relevant to you. Another feature we found useful is AI-generated comments for Unity Catalog, tables, and columns. It's well known that adding comments for developers obviously is not the favorite pastime, so it helps to have Databricks auto-generate comments that are reasonably accurate and can be edited as needed. This would also encourage the good habit of early documentation and will save developers time doing so. And finally, future Databricks-related work we've got in the pipeline, no pun intended. We especially look forward to trying out 2 upcoming Databricks features, serverless and auto-scaling. They already exist for other workloads on Databricks, such as batch workflows and DLT pipelines, but still not quite yet for streaming workflows as of this writing. We look forward to trying them out once they become available for streaming workflows. Serverless compute, for one, would help us further delegate more of our infra management to Databricks and would allow us to benefit from the economies of scale that come with Databricks' vast serverless infrastructure. It would also give us access to several performance enhancements available on serverless, such as stream pipelining, previously known as microbatch pipelining. And finally, we will continue to evaluate adopting more Databricks products where this creates synergy between them, such as migrating other adjacent workloads to Databricks and more data stores to the Databricks Unity catalog. And with that, we've come to the end of the presentation. Thanks for your time, everyone. Dongwei and I will hang around in the room for the next few minutes to answer your questions.
Thank you, everyone.